Hey Chem Kids, Campbell here. In our last video on thermodynamics and thermochemistry, I'm going to talk about entropy. So the whole point of thermochemistry is really to determine reaction spontaneity. And what I mean by that is, does the reaction happen? If I mix these chemicals together in a beaker, are they going to react, or are they just going to hang out and not change at all? So, for example, water. Does water spontaneously decompose into hydrogen and oxygen gas? So if I left water alone, would it just break apart into hydrogen and oxygen? Well, no. That would be bad if it did, right? Because hydrogen gas is explosive and oxygen gas is flammable. Wah! So the world would be on fire if that reaction happened spontaneously. So this reaction is actually non-spontaneous the way it is written. It won't happen unless we force it to happen, that we put energy in and we make it happen. However, the reverse reaction, mixing hydrogen gas with oxygen gas, will spontaneously make water. So that reaction happens, and that's better because we need water. So a spontaneous reaction is a reaction that occurs on its own. So it's a reaction that we don't have to really supply a lot of energy to make happen. So kind of like fruit ripening, right? That's a chemical reaction that just happens. Rusting. You put something outside in the natural environment and it will naturally rust. So one thing though, if a forward reaction, the way we write a reaction, if that is not spontaneous, the reverse reaction to that actually will be. So if we have a reaction like that water breaks down into hydrogen and oxygen gas reaction, that reaction is not spontaneous, but if I flip it and write it the other way, it is. Interesting. So the spontaneity of a reaction, or does it really happen if I mix it together, depends on its enthalpy, which we talked about in our last video. It depends upon entropy, which we're going to talk about in this video, and it also depends upon Gibbs free energy, which we'll talk about in class later. Now, what entropy is, it's symbolized by an S, and it's the tendency for all things in the universe to spread out. So we say that things become more disordered. Think about your bedroom, right? Your bedroom, the tendency for it is for your clothes and your stuff to just spread out in the room. Right? It takes energy to put it back together. You can also think about it in terms of probability. Like, I have a stack of papers here, and if I throw this set of papers up in the air, what's the probability that they're going to come back and land all nice and stacked together? Well, they're not, right? I throw them up in the air, and they come down all over the place. Who can I get to clean that up? Anyone need attention? So the second law of thermodynamics says that entropy spontaneously increases. The disorder, the spreading out, that's a spontaneous process. But it's clear by looking at all the papers now. So that is a spontaneous process. Now, units for entropy are joules per Kelvin. And remember yesterday when we were dealing with enthalpy, we were dealing with kilojoules. That's going to be important later. So what this means is a positive value for delta S for the change in entropy means that we're getting more disordered, that things are spreading out more, and that's spontaneous. A negative value for the change in entropy, or delta S, means that things are becoming more ordered, that I'm taking my papers and I'm putting them back into a stack. So that's non-spontaneous. I have to physically put some energy in. So next time your mom says, hey, your room is a mess, and you can say, Mom, that's entropy. It is the natural, spontaneous process. And she'll say, I don't care. Put some energy in and clean it up. Non-spontaneous. So one thing you need to know is the fact that entropies of solids are less than entropies of liquids, which are much less than entropy of gases. Gases have the highest entropy. Why is that true? Well, look at the picture here. All right, we have solids that have all this nice order, where we have liquids where we have a little bit of disorder, but gases, they're a crazy disorder. So here's this little animation. Look at, you can see the solids are not spreading out at all. The liquids, not really much either, but these gases are going crazy, right? We open the container and they're gone. They're spreading out for sure. So entropy, and make sure you know this, of gases is higher, so that's more favorable than a liquid or a solid, which is real confined. All right, so the particles are most ordered in solid phase, more random in liquid phase, but really random in the gas phase. So make sure that you know that entropy increases as we go from solid to liquid to gas. Now, another thing you need to know is that entropy is temperature dependent, right? Because remember that temperature is a measure of how fast they're moving, right? Kinetic energy. And so if they're moving faster, right, they're going to spread out faster. So higher temperature means I get greater kinetic energy and the particles move out more. And of course, more movement, right, means more randomness and greater entropy. Now, one of the things you'll have to do is by looking at the phases, solid, liquid, or gas, in a chemical reaction, predict whether the delta S is positive, spontaneous, or negative, non-spontaneous. So you're going to look at the reactants and the products and look at, are they solids, liquids, or gases? So here's a reaction of ammonium nitrate decomposing into dinitrogen monoxide and water. So notice that on the reactant side I have a solid and it becomes a gas and a liquid on the product side. So the reactants is one solid, the products is a gas and, well, 2 moles of liquid, which means that I am getting more random. I'm spreading out more, and therefore the entropy goes up, which is good, right? That's spontaneous. So we would say that the delta S is positive. All right, so just look at the states of matter in the reactants and products and see which is more random. So do we have more gases and liquids in the products or the reactants? So that's entropy. Now in class we're going to talk about Gibbs free energy, so I'll see you in class.